So this is the unit 2 for Calculus 1 at John Abbott College. Basically, I'm filming everything that I learned, so absolutely everything concept-wise in my four science courses I took this semester. And it's going to be just like really brief, well, not brief, but like concise version of everything we learned. So last video was about, well, the unit 1 for calculus. I was saying that it would be short, but it ended up quite long. It's just really because I wasn't used to it, but I'm not refilming it because it just really took a lot of time. So this time I'll go a lot shorter in terms of giving examples, and instead of like doing detailed examples, maybe just explain the concept. Last time I didn't finish talking about the derivatives because there are two ways to show, well, two types of notations for the derivatives where there is, the limit definition of derivatives. Normal one, well, normal, like the standard one, is this one as the limit of h approaches 0. This is graphically about where x is, and this is like a length h, and here is x plus h, where that is f of x, and that is f x plus h, and we're trying to minimize h. We're trying to make h approach to 0, so limit as h approach 0, and by doing that, we're gonna just like make these 2 points come really close to each other, basically ending up like super close to each other, that the distance h becomes 0, and well, there's practically no distance, so it's gonna be an instantaneous slope. So derivative is to find the instantaneous slope. Mostly represented with the letter a, but that was only one way. There are other ways to show this. This is using the h, so that's with the letter h notation. The second notation is by using really random any letter that represents just another dot. So let's say this is t. This is going to be f of x, and that's going to be f of t. T really just means any number, but then we're trying to make t approach x. So this one is going to be limit as t approach x of f of t minus f of x divided by t minus x. So this basically means that we're approaching t to x. That means t is going to be really close to x. And we're doing the instantaneous slope again, so y, delta y minus divided by delta x. And these notations are important because if you don't know them, it could seem really confusing on a question. So there could be a question that goes like limit as let's say h approach 0 of fh minus 1 over h. This here could look mixing up because we don't see a x plus h, and we see a random 1 out of nowhere, and that's kind of confusing because usually we see a x plus h and not just x. But actually, if you realize, if the x right here was 0, then inside the brackets it will just end up at h. So what this is telling us is that x is 0. If x is 0, 0 plus h is basically h, so it'll be f of h instead. And if we know that x was 0, we know that this one, which is supposed to be f of x, is rather f of 0. But then why is it a number? Because they gave us the value of f of x already. So in this case, we don't have to look for what f of 0 is. It just means that the 1 itself is the f of x, meaning that's the y value when x is equal to 0. And then the bottom is just divided by h, which is what we're used to. And yeah, that's just one of the confusing ones in the test. That actually, this is a real test question that I had. So it was like a graph, and it was like a drawing of a graph where we have to, from the image, know what this output was, and this output was 2. Regardless of what the output is, this notation was asking for the slope at when x was equal to 0. And we could know that is 0 not because from h approaching 0. H approaching 0 has nothing to do with what the x we're looking for is. So let's say this is the x value 2. And sorry, no. On the question itself, it looked like this. And it looked like this. That's like the real question we had. This is 0, obviously, and we wanted the slope right here. That's what the question was looking for. Given a dot here and a dot here, we could find the slope, which was 2. And yeah, basically you have to look at it image-wise. It's really not calculation-wise. This notation you have to understand from really the h right here. This h is the hint. H means that the x was 0, so 1 has to be the y value of x. And if we're given that the y value is x, we know, because here was 1, that there's 2 clues. The first clue is that the y value is 1. The second clue is that the x is at 0, because x plus h only gives h. So yeah, that's the 2 types of derivatives. So like I said, f of t minus f of x over t minus x of limit t approaching x, or the standard one, h approaching 0 of f x plus h minus f of x divided by h. And these are notations for derivatives using limits, but there's definitely, or actually the primary way of finding derivatives is by using the derivative rules. Like I said, you can just 3 times the speed if it's something you're interested in by just looking over it really quickly. But derivative is the unit 2 of the Calc 1. So first unit is only about limits, I'd say, and second is only about derivatives, and the third unit is only about integrals. So my CJEP switched up a little bit for the orders that they're teaching calculus for Cal 1 and Cal 2. So they brought something from some stuff from Cal 2 to Cal 1 and vice versa. So integrals, some of them are from Cal 2 depending on the CJEP, but in John Abbott we learned it in Cal 1 for my semester. So that's like my generation only. But it's only just a few more rules that are added, not that much of a big difference. So the first one is addition rule. And addition rule, well, first of all, I need to explain what derivative is. I'm jumping in too quickly. Derivative is basically the function that will represent the slope function. So let's say there's a function f of x. I don't know. It can be anything, really. It can be anything in terms of the type of function, the numbers, the powers, basically anything. And what we're looking for is a f prime or dy on dx or any other notation. So f prime or dy on dx means the instantaneous slope. So I guess you know what is a slope by now. Slope is like how steep a line is in the function. And to find that, you can actually get the slope throughout the entire function. The derivative works because you can get a new function that represents the slope of the previous one. So it's like a slope function. And this is really convenient because especially it's convenient for functions that have changing slopes. Slope that is not constant. So what is a slope that is constant? This is a constant slope. This is a constant slope. But if it is something like that, or even just this, actually that's a bit different. We're mainly talking about stuff that could look something like that. Or basically anything that isn't linear and has different slope, different steepness, or yeah, the steepness of the line, whether it's increasing or decreasing. And that's the whole concept of it, finding the slope function. And we'll use it a lot in other stuff, not just trying to find the slope. We have to first find the slope and do other stuff. So derivative is really a unit you need for not just math, not just calculus, but a lot in physics and I think sometimes in chemistry as well. I didn't reach there yet. So in addition, basically we're gonna express function with letters. So let's say you use a function and we use a function. That's the most common ones we use. This just means like 3x. Let's say this is like a 4. Actually, no, it has to be a constant. It can't be a constant. So 3x to the 2, 4x, let's say. And each of them have their own derivative. Derivative just kind of means like turning it into a new form. They have like a new form. And by combining them, we can make a new function. And it's basically twisting a function. Let's say this is the original function. We twist it into looking like this. That's kind of the idea. Every time we do something to it and there's a new function. And there is like the third or fourth or as many as you want derivatives. You can just, it's just going to be a f prime, f prime prime, f prime prime prime, prime prime prime. You can do as much as you want. And every time it will look more simple or more complicated depending on your function. And that's like the idea. It will, and going backwards also works, but that is going to be integration, and it's basically the opposite of derivatives. You don't need to know that yet. So it will be the next unit. So addition rule, u plus or minus, or addition can be negative addition, negative can be just subtraction. Let's say a u plus a v, it's just means example, 3x to the 2, and v could be a 2x. We're going to have u prime plus or minus v prime. So basically deriving each component of it. And then we have a multiplication rule. There are like two types of multiplication rule. First being the multiplication of constants. So let's just look at the multiplication of constant. Multiplication of constant is very, very, very simple. It's just multiplying. K is usually a constant. So k times u is another function. So what we're going to do is basically k times u prime. There's nothing you do with a k. You don't erase it. It doesn't disappear. It stays all along. It's just going to multiply to whatever the new partner kind of is. And then there are there's the second multiplication rule, or shouldn't call this a multiplication rule, but it's rather a product rule. And like I said, if a function has component u times v, where each of them is not a constant, it could be a 6x to the 4, and v can be a 3x to the 2. And I'm giving like x expressions, but it can totally be other stuff. It could be log to x. It could be a ln of 4. It could be a ln sine 2x. It could be as complicated as they want. And another thing, derivatives usually will be depending on how mean your teacher is or how nice your teacher is, they could give you a very, very, very complicated or condensed or detailed function. There's a sine and a tan and a ln, and it could even have a fraction. It could be an exponent. This whole thing could be exponent. It could be as complicated as whatever your teacher could give you. And I'd say it's better to practice harder ones than to practice like these really easy ones, so that you're prepared and you're used to the notation. Product rule, I didn't finish saying. Every time you derive it, you just likely would need to put a prime or make it dy on dx, just meaning that you derived it, meaning that you did some magic to it and turned into a new thing. It's not magic, but so that you turn it into a new function, not just reducing, because in many cases you have to reduce. So like the first step you do is kind of just recopying the function but making it simpler. By simpler I mean usually roots. So if there's a root, if there's a very, very complicated root, or if the root itself is a fraction under a fraction over 1, it's going to be more complicated, where it has to become like a 2 on 5 but with a negative. So this kind of cases I'd highly recommend to first simplify it before jumping into the rules that we're going to use, and before applying rules, to actually simplify it so that work is easier, and of course definitely to make less mistakes. Simplifying is totally key to making less mistakes in calculus. Even just factoring works really well. So in the product rule is going to be, this is a universal rule, u prime v plus u v prime, and that's it. It's always a plus. It's always a plus, and basically the first one prime multiplied by second one not prime, so normal, original, and then plus the first one being original and the second one being the prime. And that's it for the product rule. There's the quotient rule. Quotient rule is when you have similar to multiplication, a quotient. If a function has a component on the top and a component on the bottom, again, this could be a log 3 ln of 5x to the 2 sine, whatever it is, a component on the top and a component on the bottom. It could be as simple as 3x to the 2. What we're going to be doing is, when we derive it, f prime of x will be u prime v minus u v prime divided by the bottom squared. That's the rule. So this is the product rule. The first one prime v plus the first one normal v prime. And I still didn't explain what prime really does, but those also have individual rules. I'm definitely going to go over them, and they're really, really, really simple. I said derivatives probably the most easiest chapter in the calculus, I think. These are just rules. Just remember the shapes, so I have to memorize the shapes. Shapes, I mean, there's a prime or there's no, so constants never have prime because we'll see why. Constants are just always constant, just sticking around, and product rule is first one prime, second one not, and adding the opposite, the switching sides of who has the prime. And over here, first one has prime, second one doesn't. Subtracting, here's always adding, subtracting is only for quotient, and dividing by, do not forget your squared of only the bottom one. So it's only the bottom one that becomes squared. These all have their detailed proofs, but it is not necessary to know them for the course. As for what is prime and what does v turning into v prime look like, they have their specific rules. First one, the most basic one, is the power rule. And power rule, it's better, I think, to show examples, but the expression looks like if f of x equals to x to the m, where m is a number, so let's say 2 or 3 or 5, whatever, the f prime of x will become m times x to the m minus 1. I'd say examples are always better, so let's say 3x to the 2. Actually, no. Let's just do only expression, only an exponent expression, x to 2. X to 2, you have to bring the 2 in the front, so it's 2 times x to the 1. But x to the 1 just means x. Why did I do to the 1? Because 2, we're going to subtract 1 from it. I'm going to subtract 1 from it. So then 2 minus 1 gives a 1. So 2x to the 1. Then 2x to the 1 simplifies to 2x. Another example, x to the 3. So this is a huge exponent. X to the 3 will become, you bring 3 to the front, so 3x to the 2, because 3 minus 1 gives a 2. Another one, x to the 7. Same thing. You bring the 7 to the front. 7x to the 6. And then there's the constant rule I'd like to introduce, because it's kind of annoying not to know if you need to learn all the other rules. I think constant rule should be the first one. Although I did already explain it here that k just sticks around. It's the same principle. If there's a constant f of x equals to 3u ku. K is a constant, u is a function, so example 3x to 2. This is an expression of ku, because 3 is a k, constant, x to 2 is expression, so it's like a function. What happens is that we do a k multiplied by u prime, so I guess you can kind of see already, it's going to be 3 times. X to the 2 becomes what? We already just did it over here, is 2x. The thing is, it can be even more simplified, so it's 3 times 2 is 6x, because 3 times 2x is 6x. That's it. That's really it. It's as simple as that. And what's the habit you should get in this kind of question is, let's say if f of x equals to 7, x to the 6, f prime of x, you just directly do 42 x to the 5. Because 6 comes down and 7 times 6 gives a 42, which just stays in the front. And then 6, you do a minus 1, which gives 5, and that's the new exponent. 5 is a new exponent. So answer is 42 x to the 5. That is the power rule and the constant rule. And then we have some basic stuff. If there was a x to the 0, well, f prime f prime of x will just be 0 times x to the minus 1. Well, 0 times anything is 0, so it's 0. And that's where the constant rule actually comes from, because any constant actually could have been x to the 0. Yeah, that's something we kind of ignore, but that's true, because x to the 0 or anything to the 0 is 1. And this graphically you should understand. By the time you're reaching calculus, you understand that anything exponent to the 0 is 1. And that is because of how the graph looks like. Well, that's not why, but that could explain why. Let's say this is x e to the x. E to the x has... Also, e to the x is a graph you should memorize. I covered it in the first unit, but you should memorize e to the x graph, ln graph, or log graph. Either way. And that's because it's really unique. At x equals to 0... the value that it touches the y or the y-axis, or I should say the y-intercept, is not 0, it's 1. And when it is e for a exponent, for example, the one it reaches is going to be wow, I forgot my own graphs I was supposed to be teaching. Okay, yeah, no, sorry. E only applies for ln. So just remember that for e to the x, when the x value is 0, it is 1. And that applies for any exponent function. Any exponent function, when it touches here, it's 1. It's always 1. No matter if it is 2 to the x, 3 to the x. And that's always provable because 3 to the 0 is 1. And 2 to the 0 is 1. So when x is equal to 0, the y value becomes 1. So knowing that, the constant rule applies, because even if you do apply the product rule to the constant, it just becomes 3 times 0x minus 1. So then yeah, so this only applies for stuff that are constants. So constants, I didn't mean constants in terms of adding a constant. So if there was a function 3x to the 2 plus 4x plus 7, that is a constant. So when you derive it, you apply this product rule, and guess what happens? It becomes at 0. So after deriving, well, we can actually derive here, but 6x plus 4 plus 0 is the derived form. So this is f of x and f prime of x. So that's like after transforming our original function. You apply the product rule. Apply the product rule here as well. Well, 4x to the 1 is just 4 times x to the 0. So again, x to the 0 gives a 1. So 4 times 1 is just 4. So 4 stays. Anything that is a constant times x is just that constant when you derive it. So when the f of x turns into f prime of x. And that applies for anything. So it could be a 32, 49, 17. X turns just into 32, 49, 17. And that's also applying the product rule. Although it looks a bit different, it's the same thing. If it's to the 1, you bring the 1 to the front, subtract 1 becomes at 0. But then if there is no x, then there is you are applying the x to the 0. Actually, this is confusing. So there is no explanation you have to provide in terms of why constant becomes a 0. There was a reason. Well, it really is that if there is a constant to the x to the 0, because there's no x, the f prime will just become 0. And then so that's the product rule. Oh no, the power rule. Continued. Moving on, we have the exponent rule. And this is just straight up memorizing. If a to the x, a is a number, f prime will be a to the x itself times ln of a. And this is unique when it comes to e to the x, because e to the x, if you apply the same rule, f prime will become e to the x itself times ln of e, but then ln of e is 1. Again, ln is a function that you should memorize. That's e. No, that's at 1. The ln of 1 is 0, but the ln of e is equal to 1 when it is e here. Remember, e is a number 2 point something. Here is a 1. When the x value is e, it's a 1. So multiplying by a 1 will give 1. So f prime will just become e to the x. E to the x is a really good one to memorize. Easy one. The one, your favorite probably by the time you're solving or doing practice questions. E to the x, derive it, becomes e to the x. Do the inverse, which is integrating, still e to the x. E to the x is always e to the x and just stays along, and it's just a happy ever after. And if it is not an e, so let's say 2 to the x, if you derive it, it will have to become e to the x, so itself times ln of 2. That's it. That's the exponent rule. And then we have some trig rules. Actually, sorry, before we jump into trig rules, I think it's better jumping to logarithm rules. Log rules. Oh. So log rules is very, very easy. I'd say maybe one of the most easiest. So the notation of a function f of x or y equals to doesn't matter, as long as every time you're staying consistent. F prime of x, and here will be dy dx. So notation doesn't really matter unless the teacher specifies. So the long rule, very, very simple. You do, let's say that the long is u, okay? What are u? Prime over u. That's it. This means the function derivative of function divided by the original function. So let's say ln of 3x to the 2 plus 8x. So if that is y prime will be 6x to the 1, so it's just 6x plus 8 over the original function, so ln 3x to 2 plus 8x. Yeah, so the principle is that well, you use the notation ln u, and u is whatever the function inside it. The derivative will be u prime. Oh, sorry, no, there's no ln. It's just whatever that is inside it. So the notation just follows the rule. If there's a ln u and u is like whatever function inside, the derivative when you derive when you derive it becomes inside prime divided by original whatever that was inside it. And that works for ln of x as well, turning into a 1 over x. This is because inside is an x, so x prime is 1, and the original function is x, so it's just x. Ln of x is, this is also something to memorize, ln of x is equal to 1 over x, and you can go back and forth, but sometimes going back and forth you have to put a absolute sign, but that's for unit 3. Just memorize that ln of x is equal to 1 over x. And that can be proven by the long rule. When you do have to write down ln is when there's a double ln. So ln of 3x to 2 plus 8x, then you'd have to repeat this ln because whatever that's inside includes the ln. So that's what I was mixing up with. But yeah, that is like a more complicated example. You would probably come across it and maybe show it in this video. So log rule is the same concept, but you have to add just one more thing. Here's a log rule. Log and ln is very similar. I'd say they're even like the same thing because ln is just like log e of log. Log base, let's make up a base 7. Inside is a w. So again, inside is just a function. When you prime it, so when it becomes a y prime, it will be u prime divided by u original function times 1 over ln of the base. So that 7 come from the base of log, and you'd realize that the base of log for ln is basically log e, right? So then 1 over ln of e again is just 1. That's why this part doesn't exist in our ln derivatives. It's just in our ln derivatives, that's our ln derivative rule. It's just u prime, the inside u prime divided by the original. There is no ln something multiplied, but that comes back to reason because ln of e will just give 1. There's no point in writing that out, but that is what's happening. So that's the base. It's not always 7. To give an example, again, the inside could be as complicated as it may be. Log base 8 x to 2 plus 2x. So then whatever that's inside prime, so 2x plus 2, that's a 2x. So whatever inside prime will become 2x plus 2 divided by whatever that's inside original function times 1 over ln of 8, because 8 was the base. So the base becomes the ln of 8, not log. So the final answer for this one will be 2x plus 2 over x to 2 plus 2x. And I just write it as ln 8 in one single expression so that you don't have to separate two functions. So that's for log. Now we are finally into trigs. Trig is just memorization. And do not avoid it. It's inevitable. Inevitable because you need it so much elsewhere, not just calculus, not just Cal 1, Cal 2, and physics. So start off with basic ones. We have sine of x. So y equals 2 for everything. Sine of x, cos of x, tangent of x, tan of x. And let's go in order. Cosecant of x, secant of x, cotangent of x. There's also, yes, you have to memorize everything, arc sine of x. It's even reduced this year. Like, we don't have to know arc secant. Arc secant or arc cosecant. Those are taken out from my course, but maybe not in your CGEP. Arc sine, arc cos of x, and finally arc tan of x. Those are what we had to memorize in terms of derivatives. They're just rules and you just need to apply them. F prime equals, I'm just gonna not write f prime every time, but it just means the same thing. F prime is equal to cos of x. Just straight up memorizing. Minus sine of x and secant to 2 of x. I just forgot to mention what these mean and what these mean, so I want to remind those because it is really mixing up if you do not memorize it completely. So cosecant or secant or cotangent basically means 1 over. Oh wow, I need to make sure of that too. Yeah, so I was not wrong. It just basically means 1 over sine, 1 over cos, and 1 over tangent. Or 1 over tangent can just mean cosine over sine. And these are basically the reciprocals. They're not the inverse. These are reciprocals. Inverse is a totally different story, and those are what these kind of look like. So that's that. Inverse is when we bring from when there's equality, when you bring something to the other side, we could do like a multiplication here, division here. It's kind of similar concept, but for trig is it has its own independent rule kind of. So whatever arc sine of theta, or I should say arc sine of x, let's say x, arc sine of something equals to theta. So then that something is equal to sine of theta. That's what the inverse is doing. So sometimes we write it as sine of x to the minus 1, or a sine of x sine to the minus 1 of x. These are different because when it is sine of x to the minus 1, this means 1 over sine, like the notation says. But when it's sine to the minus 1x, so it's supposed to look like sine minus 1x, this means arc sine of x. And arc sine of x is the operation of inverse of sine. Whatever sine does, the opposite of that is arc sine. That's all you need to know. And cosecant, secant, cotangent is very simple. Just think of their names being short to whatever they're doing being simple. It's just 1 over sine, 1 over cos, 1 over tan. But then over here, inverse, when there's arc, maybe the addition of arc is a bit complicated. Remember it as sine to the minus 1 of x, and what it's doing is when you transform from one side to the other. That's basically what the calculator is doing. When you bring, on your calculator, you should see like a tan minus 1, cos minus 1, or sine minus 1. They just mean arc tan and arc cos and arc sine. And what they're doing is they're undoing the sine or undoing the cos to the theta. That's the idea. And there's derivatives for each of these, the cosecant, secant, cotangent, and to the arc secant, arc sine, arc cos, arc tan. So I'll keep those because there's space there. So as I was saying, this becomes minus sine of x. This one becomes a secant to the 2 of x. So y equals to cosecant becomes, why does it become eraser all the time? Minus cosecant x, cotangent x. Secant becomes secant x, tangent x. So the parentheses around the x doesn't matter. You could write it or not. Sometimes it's easier not to write because there's going to be too much writing. Cotangent is minus cosecant 2 to the x. And you realize that whenever you start writing something in C's, whenever you write something that has a C originally, you have to put a minus sign. So cos will become minus sine, cosecant will become a minus cosecant x, cotangent x, and cotangent will become a minus cosecant squared. Moving on, arc sine, the derivative rule is 1 over root 1 minus x to 2. Arc cos is really similar, just with a minus on the top or bottom, just a minus added to it, 1 minus x to 2. And arc tan becomes a 1 over 1 plus x to 2. And you can just apply these to whatever function you have. The thing is, when the inside of each of these trigs, so inside right now was just x all over the place, just x. But if the inside was a function, a u, bringing up was another u. Let's say it was instead arc tan of u. What you have to do is the chain rule. It's the first time I'm talking about chain rule here, but something that applies easily on this one. Basically, if the inside was not just an x and rather a function in there, meaning like a arc tan of x to 2 plus 3x. What you have to do is, yes, you apply the trig rule 1 over 1 plus, so everything squared. So x to 2 plus 3x squared. But you also have to multiply that by u prime. So basically the rule becomes a 1 over 1 plus u to the 2 times u prime. It's multiplying by the inside, whatever the function that was in it, that was plugged into, primed. So the derivative of it. In this case, u prime will turn into, we just looked at that, 2x plus 3. Because if you do the product rule, and well, this one's a constant rule, or not a constant rule, but 3x just becomes a 3. X to 2, you bring the 2 to the front, so 2x to the 1, but the 1 doesn't matter, so just 2x. That's what we're going to be multiplying. And addition rule here, something plus something, it's just derivative of that something plus something. And simplify it. Although I think this example doesn't really exist, I just made one up. It's the same principle. And for the other ones, exactly the same thing. If it was sine of u, instead it would be a cos u times u prime. It will be a minus sine u times u prime. It will be a secant to 2u times u prime. That as well. Inside becomes a u times u prime times u prime. That become u. And same thing here. So that's what I was kind of supposed to jump into now. It's the chain rule. Chain rule, the name just says it. Basically, a function could have a lot of things inside it. It could be a 3x plus 4x to the 2 plus 4 to the 2 plus sine of cos of x, let's say. And there's a lot of chain rule inside here because there is a function, a global function, and a smaller function inside it. In this case, we have a 3u to the 2. The u can be, it could be a 3x to 2 if you want. This form, but the x inside it is, instead of x, just x plus 4 to 4x to 2 plus 4 instead of x. So then what do? Do we apply the product, the power rule? Yes, we do. But then there's something in it. Do we just keep it like that? That's the difference we're going to do. Here, we're going to apply, first off, the power rule normally. So just don't care about whatever inside it and do your normal power rule. 3 something to the 2 is 6 of that something. So yes, you rewrite down everything. And if it was super long, you just rewrite the super long stuff. But the only difference is that you multiply that by now the derivative of inside of that function. So in this case, we just have straight up one expression, 1. So x, derivative of x is 1. You can do that by the power rule. X to the 1 equals to 1 times x to the 0. So it's just 1. 1 plus 8x plus 0. You don't need to write the 0. Profs won't ask you to write the 0. And that's it for the first portion. 6, parenthèse, x plus 4x to the 2 plus 4 times 1 plus 8x. And then here you add a plus sign because addition rule. Sine of cos x. So I'm kind of running out of space, but it's connected. It just keep writing, just don't have space right here. Sine of x turns into a cos of x. So then it's a sine cos of x, that's what you write first, times, you don't have to write the dot, just need to start off as a parenthesis, times whatever that's inside prime. Cos of x inside prime is minus sine of x. So this answer would look like, so y prime will look like this. And it could be as long as the prof wants you to make it long, because there could be a lot more things going on here, I mean here in the original function, they could include like 3 trigs in here and a ln and a log, and you just apply each of the rules that I just showed you into them. Something I do want to show though is the double ln. the one I just kind of messed up with at the beginning. So double ln of, let's just start off with x. So this is a ln inside a ln. That's the function. When you want to derive it, you have to apply the ln rule like you usually do. So u prime divided by u, where u is whatever that's inside the ln. So that's the u. That's all we're looking at. We're not looking at the ln. We're not looking at the whole thing. We're only looking at the u inside it. So when we look at the u inside it, here it's just x, right? No, it is not. It is the ln of x. That's the u. Because ln, there's a ln here, and then there's whatever inside it. So that is the u. You have to do the u prime of that divided by the normal u or the original u, which is just original function. So to do that, you'll have to first, it's just doing step by step. There's nothing too complicated. The rules I just explained is everything. There's no more rules to it. It's just everything. The power rule, the quotient rule, the product rule, the addition rule, subtraction rule, and the lns and logs and exponents. I showed you everything, and there's nothing too complicated, I hope. The u prime will just be the prime of ln of x. And the prime of ln of x, we apply once again. It's like a second time applying the ln rule, but it's 1 over x. Inside, ln of x has its own u prime over u. But don't really mess up too much your head. Just ln of x just turns into 1 over x, right? Ln of, let's say, 3x to the 2 will turn into a 6x over 3x to the 2. Or it can be more simplified to 6 over 3x by canceling out the x's. But the idea is the same. And then that is the top we're done, divided by the original function. The original function inside the ln is a ln of x. That is this one, this red that I just put inside the brackets. You just copy that down, and that's it. So the answer, it can be simplified, yes it can, to 1 over x times ln of x. Remember that when there is a fraction on top and another expression on the bottom, they can be merged like this. That can be explained by you doing divided by ln of x, which means 1 times 1 over ln of x, and just gives x times ln of x. This took a while for me to kind of grasp, but once you grasp it, it's automatic. When there's a fraction on top, expression on the bottom, merge the bottom with the bottom. And that is true mathematically. You can just prove it to yourself by using the normal fraction rules. Another one that I wanted to show, actually though I have to show something else before that, is implicit differentiation. Diff just means differentiation. Implicit differentiation means you're going to be incorporating y's, or g of x, or f of x, or h of x, or any other expression that is not an x. So what we're doing every time we derive is basically deriving as related to x, kind of. There's a way to say it, but x becomes a 1 when you derive it. Y becomes a y prime when you derive it. X to the 3 becomes a 3x to the 2 when you derive it. But y to the 3 becomes, you apply the power rule, because there's the power, there's an exponent. There is the power rule, but there's also the chain rule, or I should just say the implicit differentiation, but it's kind of like the chain rule here. Why? Because y is not an x, and we're supposed to derive as in terms of x. You don't really need to understand what that means, but basically we're following our derivative rules as x as a guide. X is our base and it's our guide. So whatever that is not an x, we cannot normally apply rules. So what's going to happen here, put that in green. You apply the normal power rule, right? Bring the 3 to the front to the 2. But then you also have to do sort of chain rule here, which is an implicit differentiation. Y becomes a y prime. That's it. Because we always did like u that turns into u prime, right? If there was a 3u to the 2, it would become 6u times u prime, because you have a u, which is a function. Remember how u was a function, you have to put a prime to the u. So if that u was a much bigger expression like what we just did, to the 2, you'd first apply the product rule, turning it into 6x to whatever inside it, times the derivative of the inside. So when you multiply the derivative of the inside, it's kind of the same principle when it is a y, because y, basically think of it as not being equal to x. As long as it's not equal to x, you cannot just leave it as 3y to the 2, because y is not an x. Y is the function of x, basically f of x, right? You can't go like, oh, let's say f of x is an expression. This expression 3, this expression to the 2 is just 3, is just equal to 6 times that expression. That applies if it's a x in the middle, but not if it's a function. Function, we always did the u prime thing. That's the same for trig rules. Remember how if was a function inside, instead of just the x, you have to do the times u prime everywhere. Same thing here for if the omega inside was not a x. If it was an expression, you have to do a multiplied by, well, actually this in law and log there is no complication, because you already are doing the prime, and regardless of what it is inside, even if it's a function or just x, it will work all the time, because if it was a x, it will just turn out 1 over x, because the prime of x is 1. But then if whatever that you plugged into your ln function is not a x, or not a simple expression, if it was more complicated, no worries, you just follow it normally, because x prime is already in there, or I should say u prime is already in there. The u prime is already in there. Will be the same here. If the ln of a, well, this one is a bit different because a is supposed to be a constant. It's supposed to be 2, supposed to be like a 3, like a 4. It's supposed to be like a 3 to the x in this example. But if it was a more complicated expression, we don't really use the a prime in exponents, only because we rely on the ln or the logarithmic differentiation when it comes to exponents. But the main idea is that when there is something inside a function and that is not an x, we're going to use a y prime. So all that to say that there's a y prime. So there's a repeated y. Sine of x, it's another example, will become a cos of x. If it's a sine of y, it will become cos y times y prime. Again, y has to become primed. If there is 5 to the x, you prime that, becomes a ln of 5, or I should write 5x first. 5x times ln of 5 times x prime, but x prime just turns into a 1. So no need to write 1. However, if it was a 5 to the y, then you have to do 5 to the y, which is the original, times ln of 5, so far so good, times y prime, because y turned into prime means a y prime, not a 1. But x turned into a derivative is, well, the prime of x is 1, so there's nothing to write. In terms of why you derive x but not y, or like why you have to write down the y prime and not x, it's just a rule that I followed. I never really paid attention to it, to be honest, but it just principally means what I just said. U will have to turn into a u prime because u is expression, not a constant, or not a component, not like a 3x is a component. If it's just the x, well, then it is so much different than the x to the 2 plus 4x plus 5 x to the 4. There is a lot of things to do over here, but then if it's just a number, let's say a 5, then the product, or like the chain rule, there's no chain rule to apply in here. It's all because of the chain rule. The y, there is a chain rule to apply because, well, there are stuff going on inside this y other than the x, because x is usually what's plugging into the function, and the plugging in function will give a y, so we have to prime it. So there's a logarithmic expression that I was talking about, log. General log rules you should know. Ln or log, doesn't matter, it's the same thing. A times b is ln of a plus ln of b, and it could be rewritten with logs, but you usually use ln in calculus. Ln of a divided by b. These are just normal rules that you should know from high school, but just a review is ln of a minus ln of b. Now what's interesting is if it was a lot more complicated, it could be more complicated, it could make it more complicated, but let's just not. This is just ln of a plus ln of b minus ln of c minus ln of d. If you want, you could do like a ln of c times d is equal to ln of c plus ln of d, and then like put that inside like a parenthesis, and then bring it here, and then add a zero, a negative, but then distribute it. You could do that, but you can just straight up go, if there's anything that's in the denominator of a fraction inside my log, then just turn that into a negative all the time. So that is negative because they are on the bottom. It's applying the same rule though. And this can be, like I said, as long or as short as it will be. It's really useful because you know that the derivative of ln is always u prime over u, whatever that was inside. And that's super easy compared to using a quotient rule, let's say u over v, and then you have to use the quotient rule, like uv minus uv prime divided by, and then when this expression becomes really big and really complicated, there's more mistakes, and it's sometimes quite impossible to finish because it's just getting too long. And in order to not do that much long of a calculation or like a work, it's better off sometimes using the ln rule. And this basically simplifies your log or long expression to more smaller components. And now it's just addition rule. So what you will do is a prime over a plus b prime over b minus c prime of c minus d prime of d. Basically applying the ln rule to each of them to derive it, but it's a lot simpler because it's cleaner, because you just do one of each for deriving, instead of having to mix them up and use chain rule, product rule, power rule for each component. Another thing, super important, is this. Or I should rather write it like that. Turns into simplification. It's not calculus here. It's just normal basic high school math. M can be forwarded to the front, and it's just m times ln of a, and this m can be anything. It can be a number, it can be expression as well. So ln of let's say 3x plus 4 to the 5x plus 6x to the 2 plus 5 e to the x. So this can be simplified as well. It's just simplification. There's nothing going on. It's just still y. Still y turns into 5x plus 6x to the 2 plus 5 e to the x. Just bring it to the front, and then go from there. You derive from there. And that's a lot easier because it's just a product rule now, instead of a really complicated exponent. That's why I said we don't really use like the chain rule in exponent. We do, but we'd rather use ln. Would you rather use a take the road of using ln instead? Logarithmic expression, logarithmic differentiation. So that's definitely a way to do it. Now we need to do, well, the product rule, the u prime of whatever this u is, multiplied by whatever this is, so v, plus the original u times v prime, which is the derivative of that, divided by, well, no, there's nothing to divide. And that's it. But here the thing is that this can have chain rule, because 3x to the 4 can have a 3 as the derivative of inside the function. So inside the function. Oh, sorry, no, never mind. This is a ln, so it does not have it. So if it's a ln, it's just u prime over u, and u is 3x plus 4. Has nothing to do with here. Let's use another letter. Just a prime over a. A is 3x to the plus 4, so 3x plus 4 over here. That's an a. What we're going to do is a prime over a, and plug that in as v prime, because v is like the second component we have over here. That's the first component. Yeah, so let's do an example. All of y equals to secant 3x plus log 2 x 2 minus 5 2x plus 1. This is a very long one that I got in class. And to solve it, we need to basically separate it into some pieces. Obviously, this is an addition, so it is not too overwhelming. So we have 3 components. And when there's many components and we want to go one by one and separate, like treat them separately, secant 3x, we can just directly, well, first of all, there's nothing that can really simplify further in here. There is no like a root in another fraction or anything. There's no negative roots or bigger expression. We can just dive right in. Secant of 3x tangent of 3x times 3, chain rule, plus log of base 2 x to 2, well, whatever that's inside, divided, well, whatever that's inside derived divided by the original inside interior, all of that divided by the ln of the base. So x to 2 ln of 2, and that minus, I'll write a w prime here, or actually 5 times w prime. And w is what I want to write when I have a very big expression that is too complicated to do it directly, to do the deriving directly. So just change color. Where we say that omega, or the w, is 2x plus 1 to the 3x. So then when you do a omega prime, we'd have to, actually, sorry, no. First, we're going to do ln on both sides. Why? Because we see exponent, and when there's an exponent with x in it, when you see an x in the base and x in the exponent, definitely have to do a logarithmic differentiation, or like a separate differentiation with log. So what I'm going to do is ln of this and ln of that on each side. That will give us, and then omega equals to 3x, because you're bringing it forward because it's the long rule, you're allowed to do that and you want to do that. 3x ln of 2x plus 1. Now, ln of w, we learned that is w prime over w. That's the logarithmic, the ln expression, the ln deriving. And here we have a product rule, because there's 3x, which is not a constant, times another expression. So 3 ln of 2x plus 1, just 3x turns into x because deriving, and plus 3x 2 over 2x plus 1. Yep. So that's the inside of the function derived divided by the original inside of the function, and that multiplied by 3x not touched, because the rule is u prime v plus u v prime. That's the product rule, and we just apply the rule. And then we're not done yet, because there is an omega here, and this we're trying to find omega prime and omega, or v prime with w prime. This is not a w prime yet. This is a w prime divided by w. What do? We just bring the w to the other side, so that it just becomes w prime equals to w prime equals to w times everything here. So then what we just need to do is to rewrite your w. That's why it's better to do all your work clean, so you remember what is w. W is a 2x plus 1 to the 3x. That's like the original function before deriving it separately. So this is the w before it was primed, times, be careful with parentheses because you have to include them. That's not a t, that's a plus. And here 3x times 2 over 2x plus 1 can be simplified to 6x over 2x plus 1. I will have to put the parentheses over here because there's an addition, and if you didn't put that, that is an error. That's a mathematical error, and you'll lose point for that. And now what we're going to do is plug in the w and everything here in there. plug in, I mean just rewriting it. Just rewrite the w omega prime as this very long expression. And what you need to do is just rewrite y prime equals to secant 3x blah 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 minus 5, and you rewrite this blah blah blah. I'm not rewriting that, but you understand it, hopefully. Another one, it's the same type of question, but let's do a simpler looking x to the x to the x. That's a question that my teacher made us practice. So now we have basically double exponents. Y prime, like always, just start off normally. Cos of x to the x to the x. That's the first step, because we first want to do the overall deriving. Overall, this is a sine of x. But then there's stuff inside it that we have to derive and multiply. Whatever that u is inside. But this u inside is a x to the x to the x. So it's not as simple as just u is equal to something. In this case, you have to do a double substitution, kind of. Substitution, or I should call like a double draft. What's going to happen is, well, this is just the first step, sine turning into cos, because that's the derivative of the sine. Whatever inside is still remaining, because we don't touch the inside yet, and then we start touching the inside. I'll just put an omega prime again. It could be h, it could be a, it could be b, whatever you want, but we just use w, which some people call omega. And then you have to write down again here, omega is equal to x to the x to the x, right? ln of omega, you do the same thing, but now is it like this? Or is it like that? Which is a really good question. And let me tell you, it's actually x to the x to the x. It's like that. So, like this, basically. You want it to be as simple as possible, and to turn this into something as simple as possible, you want to do ln of omega equals to x to the x, ln of x. Instead of not x times ln x to the x, because what's the point of turning into a ln if there still is an exponent? If you want to get rid of the exponent, it's better to bring everything to the front that has more exponent. So right now these guys have more exponent, but ln only has the x as expression inside it, so it's cleaner. Now we have ln of omega equals to x to the x times ln of x. We just keep going with the same principle. X to the x, again, we're going to go like a v prime. And where v prime, or we should just say v over here, v is equal to x to the x. And that's simpler. ln of v is equal to, bring the x to the front, ln of x, just bring that to the front with the ln in it. And this one turns into v prime over v is equal to, this is a product rule. If you see it, component under component. So 1 times ln of x plus x times 1 over x. So 1 is the prime of the derivative of x times ln of x normally, plus normal x times the prime of ln of x, which is 1 over x. And 1 over x times x is just 1. So v prime over v is ln x plus 1. And you just bring v to the other side while putting that into the parentheses. V prime is equal to ln x plus 1 times v. And v was originally x to the x. So nothing was new in here. We're now going to plug that in inside this v prime. Let's say that we just still didn't know what v prime is. Let's keep going with v prime so that we can do them individually, but we know here that v prime is that. We're going to do omega over omega, or w prime over w is equal to, well, I should actually write just v. V prime, we know that it becomes, yeah, so we know that it becomes a v prime times the original function, so ln of x, and then plus whatever v was originally times the prime of ln of x. The prime of ln of x is 1 over x. All of that into parentheses with the omega or the w coming over here. So we have w prime is equal to v prime ln of x plus v times 1 over x, all of that times w. So w originally was a x to the x to the x, so x to the x to the x. Now we're going to substitute everything. I'll rewrite this one so that it's clear. So we have that where there's a omega, where there's a w prime, and the w prime is this. And there's also v, where v is this, and v originally, I forgot to transcribe it, but v originally was a x to the x. Turned into this huger, bigger one. So y prime, we'll just rewrite everything, x to the x to the x times w prime. W prime is here. So v prime is there. Ln of x plus 1 times ln of x plus v is just x to x times 1 over x. You can simplify this one. And all of that times x to the x to the x. And that's the answer. I feel like I forgot something. Oh, sorry, I forgot to put the x to I forgot to rewrite the x to the x. So yeah, that's the answer. You're gonna have x to the x times ln x plus 1, that's v prime, times ln of x plus v itself, origin x to the x times 1 over x. And x to the x to the x, there's so much x's, but that's the final answer. Now there is implicit differentiation where I talk about y turns into a y prime. We're going to be doing that, but instead of really simple version, they're going to become a bit more complicated in terms of expressions. So let's do this one here. For example, 4y to the 2 minus 8y plus 7x minus e to the xy equals to 3x to 3y to the 7. So what you have to do is apply the normal rules with y's included, and then you have to separate to find y prime. That's usually the question. The question is find y prime. So doing it really quickly, it becomes y prime minus 8 plus minus 8 y prime plus 7 minus e to the xy is just e to the xy itself times the prime of the power. So in this case, it's the product rule of xy, 1 times y plus x times the prime of y, so y prime, is equal to, keep going, 9x to the 2 times y to the 7 plus original 3x to the 2 times, well, 7y to the 6 times y prime. And what you want to do is to isolate y prime, and there's y prime a little bit everywhere. So you want to distribute the minus e to the xy. So 3x actually can be simplified further, but most of the cases teacher don't really ask you to simplify it. Now what we want to do is to group them. To group the y primes. There's another y prime here and another y prime here. Bring all the y primes on the one side, and whatever that's not one prime on the other. It's a lot of writing. So now we have everything that has y prime on this side. That's a prime. Is that a prime? No, that's a 7. Sorry. Sorry, let me just rewrite that. Okay. Okay, so it turns out to be y prime 8y minus 8 minus x. Yeah, so now I brought whatever that was on the y prime to one side, and the other side we have so that is, well, just isolating y prime out of everything that you originally had a y prime. So there was 8y prime, 8y prime, and ey, I think I forgot a y prime here. That's not a 6, that's a y prime. That's a y prime, so e to the xy x, and then this one. This one, not like that, not like that. Like this had a y prime, and everything else that doesn't have a y prime on the other side, and all you have to do is just divide it. All of that, just divide it by whatever that's on the other side. Is equal to y prime. It is a very big work to do, I'd say. There's a lot of rewriting and like messing up, and it could totally go wrong if you forget one of components, or forget the chain rule. But always remember your chain rules. Always make sure that everything inside is cleared out, like you did everything in the inside of a function, and don't mix up with your y. Sometimes there's a y prime. Sometimes there's two y's that you have to write. One is normal y and another y prime. This is when there is a chain rule. And sometimes it's just y prime itself, because 8y, for example, turns into 8y prime. 8y prime, yeah. Moving on, there are many questions where they ask you for the tangent line question, or the horizontal tangent, where horizontal tangent or horizontal line is equal to 0. So the slope of a function is 0. So like this kind of, let's say this is f of x, where the slope is at 0, or where the horizontal tangent line, the slope is equal to 3x. Or they could just give you an equation, or they will ask you for an equation given that a function is like this. And they could also give you at x equals to 1. So what these questions are asking is, what is the slope and what is the equation? Or what is the equation when slope is equal to 0? And that is really easy to find. What is the equation when the slope is equal to 0? You just need to find the new function where it's f prime of x. And there's a new expression you find. That expression, you turn it into 0, and you find what x is. And by finding what x is, since you have, well, the slope of the function from finding the f prime, and you have some points that are given. Usually they will give a y, they will give you an x point, a y point, and you'll have to find out, just back calculate the equation. Or even simpler over here, it's just finding the slope from deriving, because deriving you'll find the slope, and they'll give you x coordinate or y coordinate. And you're also looking for the the equation, and by plugging in these equation with a slope, you will be able to find the equation. That sounds complicated, but it really is just y equals to ax plus b. Like, how many times did you see that? It's basically a x here, a y here, that are values that are given. A is the f prime. It's what we've been doing in this whole capsule video. It's the slope of the function, but it could be the slope of the function at when x is equal to something, and x equals to, let's say, minus 2. And b usually is the one you're looking for. You're finding b. But again, b is fine. You can find b easily because you have a value of y, you have a value of x, and if you found your f prime, just by plugging it in, you can find your b. I won't do an example, but that's the the basic idea. There's nothing too hard behind it. It's just playing with your slope that we found and adding it into what we learned in like 3rd year of high school. This is like third year high school math. The one thing you should always do is to find your xy coordinates. If they only give you the x, for example, you just straight up go find the y from the original function, because they will always give you the original function. Or if they're doing the opposite, if they give you the slope function, so they could give you the slope function, you can just try to find, you're looking for the original function, but then they give you the slope, they give you the b, they give you the a, of course, because it's the slope, and then they give you a y. So what you need to do, basically, well, in this case will be integration, but if it's not integration, you just play with your slope and a and b, trying to find either one of them. It's really not hard. Horizontal tangent, when the slope is 0, is a horizontal tangent. Horizontal tangent basically usually is when there's a local minimum or a local maximum. Local minimum meaning it's like the minimum of a function or like a maximum of a function, but it's the local because there could be a more negative or a more positive function throughout, but when we're in the region that we're looking at, that is like the maximum. That's what we call it, local maximum or minimum. And this one is even more simple. It's just a function, f equals to something. F prime, you turn it into a new function, set that equal to 0, and look for x. That's really it. But there are some of them that could look not too obvious. Stuff like this. Turning it to f prime of x will become 3x to 2, ln of x plus x to 3, and this one's going to become 2, 1 over x. And then you have to look for where x is. What x is. What x is for it to become to 0. Because we're setting it to 0. We're setting it to 0 because slope at a horizontal tangent, like a slope here, that slope is 0. Because this is the incline, and if the incline gets smaller and smaller and smaller and turns into a straight line, well, that incline is at 0. That slope at that region, that instantaneous region, is at 0. Oh, what is my race? Here is a 0. That slope is at 0. Slope being 0 basically means f prime of blah 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 is set it equal to 0, and look for the x. Look for the x for where that slope is 0. So then here, you always need to factor. That's what I'll tell you. Always factor when looking for the tangential horizontal tangent. And we can factor easily here. Take out x to the 2. We have 3 ln of x to 2 plus 2. Well, I should have simplified it further before. So this can be simplified to x to 2. And yeah, taking out x to 2, we have 3 ln of x to 2 is equal to 0. And then you don't need to bring one to another side or like subtract or anything. No, don't. If there's a product of something times something turning into a 0, then that has to be a 0, and this has to be a 0, or either one, either or. So x to 2 is equal to 0, that's obvious, x has to be equal to 0. If 3 ln x to 2 plus 2 equals to 0, well then, first of all, it has to be equal to minus 2, and then x to 2 has to be minus 2 over 3. And then, here's the tricky part, you just need to play with ln and e's. Because we know that ln of something, and of y, let's say ln of y is equal to 7. We also know that ln or log of y is equal to 7. And with the base and the product, or I should say the power, either way, whatever the 7 is, e to the 7, we know that has to be equal to y. So then if you have ln of y, we do ln on each side because we want a ln of y. If ln of y is equal to ln of e to the 7, well then y is equal to e to the 7. And if we know that ln of e is 0, well, actually, no, 1. If we know that ln of e is 1, and we can bring 7 to the front, well, 7 times 1 is just equal to 7. And that is equal to ln of y. So that is a way to do it, but you don't need to go too complicated when you're mixing up many expressions. That was just an example, but if there's a ln x to 2, well, in here we can do 2 ln of x equals to minus 2 over... Actually, no, it's shorter writing it e to the minus 2 to the 3, applying the same rule, is equals to x to the 2. And then if you have x to the 2 is equal to e to the minus 2 to 2 over 3, x is just equal to root e to the minus 2 over 3. Yeah, so that's also from I'd like to do. Imagine that there is an e, and then we know that this exponent that will have to give that. So naturally, e to the minus 2 over 3 has to give x to the 2. That's also a shortcut. It's like a shorter way to do it. So whenever you see a ln of x, it's basically a log base e. So then if there's a log base anything, log base 2, 8 equals to 3, well, you know that e to the 3 equals to 8. So 2 to the 3 equals to 8. So same thing for ln. So if there is a log e x to 2 equals to minus 2 over 3, well, e to the minus 2 over 3 is equal to x to 2. So e to the minus 2 over 3 equals x to 2. And you isolate x, and that gives this. And there is basically no much more to the deriving chapter. There is the related rates and the sketch curve sketching. But related rates, they are just word problems that imply different derivatives. There's the slope, there's the increasing rates for each component. They could give you like a cone, and they're looking for the height when the what the height, how the height, so dh on dt, how fast is the height changing. The height is changing when the radius is changing at the rate of 5 meters per second as the pyramid gets bigger. The pyramid could get bigger, and they could be telling you one of the rates. It could be a volume, it could be a radius, it could be a height, and you just combine whatever formula that works, that is true. You always want it to be true. You isolate the variables that match, so it could be from knowing what volume is. You are given what the volume is, and you want to first isolate what r is as of expression. You're looking for what r is as of expression, so then you can isolate r is equal to expression, and you can rebuild the original formula, the original function, because a formula basically turns into a function in this kind of case. And then you rewrite the function with a new r incorporated. What you want to do is to v prime, because you want to derive it, and derive the other side as well. So r times dr on dt, because you're deriving with respect to one of the component, depending on what component you're looking for, and just keep writing with the additions or subtract or multiplication or chain rules, other components that are in there, and you have a certain amount of knowns and unknowns, and you'll basically want to isolate one unknown from other known values that are given from the problem. Let's say that's just a brief overview, but we could do one with related rates for the cone. Let's say the problem is, let me just read it out. So the trunk of a tree has a conical shape, and its radius changing at a rate of 1/10 meters per year. So So the rate of change of dr on dt is 1 over 10. The height of the tree increases at a rate of 2 meters per day. So the h on dt is 2 meters per year. Did I say day? And then we want to look for the change of the volume. So the v on dt is what? When the height is 50 meters. And they will usually give you the formula of the volume. So right now we have the change of r, the change of h, and then we're looking for the change of v where we are given h. It's quite solid. I hope this is obvious. Like, they're giving us a lot of information. So v equals to pi over 3r squared h. First, we want to eliminate r. So by eliminating r, basically, you want to change r into another expression. So if we have, well, not eliminating r all the time, but if we derive it, this is like my first step I usually always do. Sorry, we don't eliminate r. That's another case. So in this case, we just do dv on dt. First, just write down whatever you have right now. Deriving it normally was what you're supposed to usually do. So this one, this is a constant. Pi over 0 is a constant. 2r, bring it forward, and we have a dr on dt because we want it to be prime and it's not with respect to the time, because we're doing with respect to time over here, times h plus r to the 2 dh on dt because we want the h to be derived, r to be derived. And they are both given dr on dt and dh on dt, which is given in the problem. And then we have also that the height is 50. If we know that the height is 50, actually, we don't need to find the radius. Sometimes we don't need to find some stuff. And in this case, we don't need to find the radius at all. You don't need to know the radius when the height is 50 at all. So dv on dt is still what we're looking for. 2 times the radius. Oh, actually, we do need to know the radius. The radius is 1. Did they give the radius? Oh yeah, sorry. The problem did give the radius. I was wondering why there was not the radius. There is the radius, so they gave us even more information. So we have the radius. We have dr on dt, which is 1 over 10, times 50 plus radius to the 2 is still 1, times dh on dt is 2. Basically, you can see that it's just plugging it in, plugging numbers in, and then dv on dt we just calculate. That gives us 4 pi. That's it. And it could be triangles where they will tell you there is a h here, there's a x here, there's a y here. The x is changing at a rate of 3 meters per second. It's increasing. Y is decreasing 2 meters per second. At what rate is h changing? Really similar type of situation, because there's a function over here. This is a right triangle, so you know that x to the 2 plus y to the 2 is equals to h to 2. From here, we can do, so the derivative rules is equal to, well, h to 2 or 2h and dh on dt. You can just always use derivative rules and then plug in what you know to isolate what you don't know. And usually they will give you enough information to be obvious, but sometimes it isn't obvious, and when it isn't, you just need to solve for one. They will tell you when h is equal to 7, let's say, or actually, let's say when h is equal to 5, and then there's the y that is equal to 4. So then they will tell you what is the dh on dt. Well, you actually do need to know what x is, but then it is totally possible to find it, because x to 2 plus 4 to 2 has to equal to 5 to 2. We can calculate that x is 3. So sometimes you have to come up with the numbers, just like how I was trying to look for the radius. But if you need to look for stuff that are not given, most of the time it's findable, and that's from other knowledges such as the Pythagore in this case. So x, you find it by yourself, and then you plug it into a similar equation looking like this. But make sure that these equations are not wrong and that you do the derivatives properly. So that's Related rates basically means related change of, well, how fast something is changing, that is related or has to do with what other stuff will change according to it. So if there was a triangle like this and the height is never changing, let's say it's a ladder, the ladder that's sliding down to the ground. So as the ladder slides down, the y decreases but the x increases, right? So there's a relationship between x and y where h is constant, and usually if h is constant and then we're given other informations, we want to find first what h prime is, but the h prime will turn into 0. Sometimes you could play with that because a constant derived is always at 0, and that makes everything easier because it will just cancel out the whole h, and it's just the relationship between x and y that we're looking for. But the relationship between x and y is a Pythagorean that includes h, so our calculation does make sense. And the last one that we're gonna have to go through for Unit 1 is the curve sketching. So the curve sketching, I will not go in detail about it because it just takes literally 20 minutes to just do one curve sketching problem, and I think it's already long enough. Unit 2 will end with curve sketching, but basically you need to know your derivatives, and that's it. It's because you're looking for domain, the x-intercept, the y-intercept, and horizontal asymptote, vertical asymptote, increasing sections, decreasing region, increasing region, your local max, your local minimum, and your concave up, concave down inflation points. This one is from the original function. These are from your f prime, so the first prime of your function. These are from f prime prime of the function. And every time you will find the coordinates or like the dots of, let's say, a maximum from the original function. Minimum as well, you find it from the original function. And even here, concave up, concave down, you will find their regions excluded or included. You usually doesn't really matter, usually just excluded all the time. But they are also found from original functions. And what this means is to be plugging in your x and y's, usually x, into the new derived function that you found. So like the slope function, you just plug in the x into the new f prime or the f prime prime functions that you found. So what x do you find? What x do you find? That is what you have to memorize remember for curve sketches. Anything that's equal to 0. F prime of x is equal to 0 or does not exist. F double prime of x equals to 0 or does not exist. Whatever these x values are, there could be 1, there could be 2, there could be 3, and probably won't be 4 because it's just going to be too much work. Every time you find a fx or f prime of x, well, usually they will give you, good news is that they will give you the f of x in the problem. They will give you the f prime of x, they will give you the f prime prime of x. But every time you come across these sections, just section 2 and section 3 especially, just need to turn f prime, turn it equal to 0 or turn it equal to d and e, meaning divided by 0. This means just divided by 0. Whatever divided by 0 does not exist. So just turn the denominator into 0, and that will be the x you're looking for. So denominator, let's say the denominator is x to the 2 plus 2. That equal to 0. So x to 2 equals to minus 2. Oh, now there is like a square root of a negative number. That means there is no d and e, and everything exists. So in this case, there's no d and e. If it was instead minus 2, then x to 2 is equal to 2. So x is going to be plus or minus root of 2. So there are 2 points possible. Equals to x is equals to 2 root or x equals to negative 2 root. So these are the points that you're going to be testing, plugging into them, and see if that dot exists, that point exists in the original function. You're going to be repeating that for the increasing, decreasing, max, minimum, concave, down, and inflation points. And one other thing to know is when it is increasing, it will be a positive value when you plug in the f prime of x. When you plug in the f prime of x, finding these critical values of when f prime is equal to 0 or that the function does not exist, they will give you either a plus or a negative when you plug it into the slope function or the slope function. And if it is a positive, then that's a concave up region. If it is a positive, it's a increasing region. If it's a negative, it is a concave down region, meaning that it looks like this, or that looks like this. And if it's a negative, it's obviously a negative, so decreasing slope. And we could do an example, but it's going to take too long. So that's the concept. For domains, it's whenever the function does exist. So try to look for when it doesn't exist. Same exact principle. When the function is equal to 0 or the function does not exist is, well, not actually, no. It's not the same exact same thing. For the first one doesn't matter. So domain is when you're trying to look for where domain does not exist. So just turn the function into when it does not exist. It could be x to 2 plus 4 divided by 4x. So the 4x cannot be at 0. So whatever x equal to 0 is, well, the function does not exist there. So in this case, it's going to be r except for it's 0. It could be a ln, it could be a root. So inside of a ln or root, nor can be negative, and for ln cannot be 0. There are other rules, other circumstances that the function won't exist, but you just kind of have to try to find out when it doesn't exist. Usually it's when the denominator is 0. Just remember, denominator is equal to 0. The function does not exist. X-intercept, y-intercept, you learned them in high school, but turn x equal to 0, y equal to 0, sorry. And this one, turn x is equal to 0, and you will find those points. Horizontal asymptotes is from the first chapter, but it's when limit as x equals to plus or minus infinity. You find your x values there. It's in the first capsule video. Vertical asymptote is c over 0. So when the denominator is 0, same process as the domain. Max and minimum is just plugging in your values that you found from doing when if prime is 0 or d and e. And if they do exist in the function, the max or the minimum exists. Sometimes it does not exist. So if it doesn't exist, then there is nothing in the max. The maximum doesn't exist, the minimum doesn't exist. Inflation point, same thing. If you find your either f prime is equal to 0 or d and e, whatever those values are, you plug them into the original function to find the points, but sometimes they don't exist. If they do exist, it is an inflation point for the points that they transfer, like they change. And there's one thing you need to memorize for max and minimum. It has to be a transition point. So max has to occur when it is turning from increasing to a decreasing. It can't occur between an increasing and an increasing interval. Like you find these critical points, but whenever the region is turning in from turning into opposite direction, then there is a potential inflation point or a maximum or a minimum. That's kind of a logic, because if it's going up and down, there's definitely a maximum. There's going up and up, there's a minimum. But there won't be a maximum when there's going up and up, or when it's going down and down. There is no minimum or maximum here. It is not a minimum or a maximum. I'd rather not explain because it's gonna be too long. Curve sketching, better go look into other websites or videos or textbooks. But those are the concepts. And yeah, that's it for Unit 2.